Hi everybody, welcome back to another fun-filled week of calculus. There's a lot going on in this video. It'll probably be another long video, so feel free to watch it in pieces. You may not decide to watch the entire thing all at once. But without any further ado, we're going to take a look at a lot of different things this week. Radicals, I want to review rules about how to write a radical expression with exponents, how to do a quick polynomial division by a monomial, and then we'll get into the calculus stuff. Okay, so for example, with radicals, okay, x to the m divided by n, where n is not 0, this is exactly equal to the nth root of x to the m, or you can do the nth root of x and raise the entire thing to the n power. Now, you can't do the 0th root of a number, right? That doesn't make any sense. So, of course, the fraction is undefined when the denominator is 0 anyway. But this is going to be a helpful thing when we are doing calculus. So, for example, say, you have to do, I don't know, like the 5th root of x cubed, right? You can rewrite that as x to the 3/5 all day long, right? 1 over the square root of x can be written as x to the negative 1/2. Because as you know, if something's in the denominator and you move it to the numerator, it switches the sign of the exponent, right? So just real quick, I wanted to, kind of review that with you. So that deals with that topic. With dividing by a monomial, this is another helpful thing when we do derivatives, and soon and very soon, my calculus students will be very happy because they will learn how to find derivatives without using the limit definition, which was a big pain recently, right? Having to do so much math to do a derivative. There are actually some rules, and some of them aren't simple, but we'll talk about those in a minute. So, okay, let's say that you have something like this. We have x squared plus 2x plus 1, and this is all divided by x. Okay, when you have a polynomial divided by monomial, you can divide each term in the numerator by the monomial. So you are technically doing this, the first term divided by x, and then the second term divided by x, and then the third term divided by x. Well, we all know that the first term is actually x. As long as x is not 0, we can say that, right? And then for x not equal to 0, these two things become 1, so this simplifies to 2. And then 1 divided by x, we can just rewrite as x to the negative 1. So you can write many things with exponents. X to the 1, of course, when there's a constant, we say that really, without even thinking about it really, next to that 2, there's an x to the 0, right? And this is technically x to the 1. So I want you to think of different algebraic expressions having the power of x. Whenever that's possible to write, it's going to be to your advantage to do that in calculus. Okay, so just very, very strongly encourage you to be able to implement these algebraic rules. Okay, now why is this not erasing? I'm not sure, but in any event, let's just say, and my computer doesn't want to cooperate, but let's just say that we have an expression like y equals x squared, right? Wouldn't you want to know a simple way to find the derivative of this? And furthermore, in a little bit, we kind of like, how do we even call the derivative of y, right? There's a couple of different ways to do it, and if you haven't seen this yet, you will very soon. So one way to talk about the derivative of y is to call it dy dx. This notation is due to a mathematician whose name is Leibniz. And I'll show you the Wikipedia page where this is a thing in a moment. You can also talk about the derivative by using prime notation. So you could say y prime. This notation with the prime, or we say prime, it's really kind of like an apostrophe, sort of. The prime notation comes from another L guy. His name is Lagrange. Lagrange was a little bit after the time of Leibniz and Isaac Newton. They're kind of considered the founders of calculus back in the 1600s. Lagrange came a little bit later 1600s, early 1700s. But these are the notations that have survived to this day in calculus. And both of these, the derivative of this expression x squared with respect to x is 2x. And I'm going to show you why. I'm going to show you why that happens. I really would like to be able to, yeah, there we go. My eraser is working now. I'm using something called Epic Pen on a Mac, and the Mac version of Epic Pen is not as good or as robust as Windows, but it's what I can use on my Mac Mini with my trackpad that I'm writing with, right? So that's what I got. That's what I got. Okay. Trying to get the eraser tool to work. Okay. All right, so I'm just going to erase everything, and we'll show you the derivative notation and some rules in a moment. So let me just erase all this stuff, and let me go show you the Leibniz notation, right? Leibniz notation, there's a Wikipedia page on it. I'll try to link it in the video description. But in Leibniz notation, he would call dy dx the derivative. And then there's another one with a d2y and a dx squared. That's called the second derivative. So we'll talk about that if you noticed in the earlier part of the video. That's repeated derivatives. That is something that we're going to talk about before this video is over. Okay? All right. So next item up for bids, like how do I find, how do I know that the derivative of x squared was 2x? Well, the first rule, rule number 1, is called the power rule. And the power rule says if you have any power of x, that the derivative, we'll use Lagrange's notation, y prime, is what you do is you take this power and put it in the front, and then you take the old power and you reduce it by 1. So what's happening here, okay, is we'll do y prime, and then we're going to take that 2 and put it in the front, and then we're going to reduce that power by 1. The end. The derivative is 2x. And if you were paying attention earlier, you'll notice that there are many things that we can use this rule for. So, for example, let's say that we have f of x equals the square root of x plus 3 over x. And we want to find the derivative like really quick, right? So I can write this f of x as x to the 1/2, because technically there's a 1 there and there's a 2 there. And then 3 over x is 3 times x to the negative first power, all right? Now using this, I have a power, right? And they're a real number, so I'm going to cross over the algebra border into the calculus land. Okay, so there's kind of like a divide here. And I want you to pay attention to this. If you're a calculus student of any kind, whether you're one of my students or not, I always tell my students to do algebra first to try to simplify stuff algebraically. But then when we do calculus, you're creating a different thing. It's a different species. It's a different animal. It's a derivative, right? So this is going to be a different function, and we'll use the power rule to do this. Now, how did I get that? I moved this down in front, and then I subtracted 1 from the exponent. I'm going to do the same thing on the next part. I'm going to move the negative 1 out in front, and I'm actually going to multiply it by 3. So that's going to be plus negative 3, and then I'm going to reduce by 1. So even if there's a constant here, even if there's a constant in front of this, say c times x to the n, then you just multiply your c times the old exponent. You move n times c, right? So that's kind of what we did here. We took -1 and multiplied by 3. Okay. And then, of course, if you'd like to, if you need to, you can clean this up and you can rewrite this as 1 over 2 squared x minus 3 over x squared. Okay. So this is called the first derivative of f with respect, and my handwriting looks terrible, I'm sorry. I'm still getting used to this writing tablet, with respect to x. Okay, so f is a function of x, the output depends on the input, and x is the input. So we're taking this derivative with respect to x. This idea of respect to a different variable will come up in later topics in calculus. So you might take the derivative with respect to time, or with respect to y or z or some other variable, theta, right? So it's important to understand like what input variable you're working with. And in calculus 1 and in 2, to be honest, we usually say that this is calculus of a single variable, right? We're doing the derivative with respect to a single variable. This is called single variable calculus. So again, this is one thing up here. This is a function, what you're used to in pre-calculus algebra, right? Or other math classes. You can graph this, you can talk about the asymptotes and the end behavior and those kinds of things. But now there's a whole different function, and it's called the derivative. And you're hopefully starting to figure out why the derivative is useful. It helps us with instantaneous rate of change and velocity and other things, the slope of the tangent line, right? Okay, so just really, really important, right, to utilize some algebra rules to get things written in terms of powers, and then to use the power rule. And of course, this ending part is optional. You don't have to write this unless you need to. So if you're one of my students and you left it like this, I'd be just absolutely fine. That is mathematically correct. Okay. All right. Second rule up for bids is what happens when that doesn't work, right? So this is called, and this is in section 2.2 of your text if you're one of my students, this is called the product rule. And the product rule is the product of two different functions that are multiplied together, right? So we'll say that y is defined as a function f of x times a function g of x. Okay, how do we find the derivative of this? How do we do the first derivative? And by the way, the second derivative is the derivative of the derivative, if you want to scoot to the end of the video to see more about that. That's something we'll talk about in a little bit. But here's the way that the derivative of a product works. There's a rule involved. This is a rule, so write this down, commit it to memory. You're going to need this throughout your calculus courses. Super important rule. I put it on an index card or a sticky note and stick it on my computer right now. Okay, so it's the derivative of the first times the second plus the first times the derivative of the second. Now there is some heavy-duty algebra that's involved. You can use the limit definition of the derivative to prove this, and there is a proof in your textbook if you're one of my students. I've also written this proof before, and it is very involved. It takes up about a half a page of typewritten text. But if you're interested, let me know. I will tell you where that is in your book, or I will show you how to do that. But for the rest of us, just believe me that this works. Okay, so let's say that we have a function, right? Let's say that, okay, there's our rule. All right, so what if we have a function that is the product of two things? Let's say x squared plus 1 and x cubed plus x plus 1. Okay, so we can use the power rule to do this. The problem with the power rule is that you would have to multiply all this stuff out first, right? And I'm actually going to do that, but I don't want you to do it. I don't want you to do what I'm about to do, and I'm making a point, okay? So I'm going to stay in the algebra land. I'm not doing calculus yet, but I'm going to distribute everything out. So I'm going to do x squared times x cubed, x squared times x squared times 1, and then I'm going to do 1 times x cubed, and then 1 times x, and then 1 times 1. Okay, so all this stuff multiplied out is x to the 5th plus 2x cubed plus 2x plus 1. Okay, so that means that the derivative, y prime, if I use the power rule, which was a few minutes ago in the video, if you want to rewind to that, I'm going to move the 5 out in front and then reduce by 1. I'm going to move the 3 out in front. 3 times 2 is 6 and reduce by 1. There's a 1 there, so let's think about what happens there. 1 times 2 is 2, and then I'm going to reduce by 1. Wow, x to the 0. And then the derivative of a constant is 0, and here is the reason for that. Here's the reason for that. Technically, there's an x to the 0 here, and 0 times 1 is 0, and it would be 0x to the negative 1, but we know 0 times anything is 0, right? So technically, this is just 5x to the 4th plus 6x squared plus 2, because this is equal to 1, as long as x is not 0, and this is equal to 0, right? So this is 2 times 1, and then adding 0, right? So that is our derivative crossing over the calculus line, right? So this is our function, this is our derivative. Now let me show you what would happen if you were to use the product rule. Whoops, I did not mean to do all that. Sorry about that. I thought I had gotten a good handle on when that kind of thing was going to happen. I tried to learn my lesson in previous videos. All right, so I can just go straight into the calculus land. Here's the way I'm going to do this. Okay, I'm going to call my first function f and my second function g. Now, what I need to do with the rule is I need to take the derivative of f. So the derivative of f is 2x. And remember, the derivative of a constant is 0. We talked about that. So this is just going to be 2x. So my f prime is 2x. Okay. So I have to do f prime, which is what that is, times g. All right. So let's go do all that. And then I have to add f times g prime. And what is f? Well, f was the x squared plus 1. And what's g prime? G prime is 3x squared plus 1x to the 0 plus 0. So that's just 3x squared. Let's think about this for a moment, especially since this is new. The derivative of x to the 1 is 1x to the 0, or just 1. And if you think about it, y equals x, the slope of that line is 1, right? So remember, the derivative represents the slope of the tangent line, or in this case, the whole line. The derivative of 1 is 0. Okay, so if I were to multiply this out, you think I get that pink thing, right? And it actually works out. It works out. Okay, so let's do the math here. I've already have the derivative, but I'm going to go ahead and multiply it out. So I have 2x to the 4th plus 2x squared plus 2x. And then I'm going to do the other distributive property, which is kind of the FOIL method. So that's going to be 3x to the 4th plus x squared plus 3x squared plus 1. And if I do all this stuff, let's see, I've combined like terms, so I have a 2x to the 4th and a 3x to the 4th. So that's 5x to the 4th. Sorry about my sloppy equal sign. And then what have I got here? I got 2x squared and another x squared. So that's 3, and 3 more makes 6. And then I've got my 2x there. which looks kind of weird. Really shouldn't be a 2x there, and then I've got a 1, right? So, oh, you know what? Totally messed up. F prime G plus F G prime. This, earlier, I messed up. This was actually x squared, right? X to the 5th, so if you caught me earlier in the video and you hung in there with me, alright, this is x to the 5th, x cubed, and x squared, and then x cubed, x, and 1. So actually what this is was wrong. This is x squared plus x, right? Which means that the derivative here was all messed up. So let me go fix that earlier work. So what's supposed to be here? This is supposed to be the derivative of x squared is 2x, and the derivative of x is 1. So this is actually supposed to be 2x plus 1, and that is exactly what I have over here. Okay, so we learned that Mr. Molekash is human. He made a mistake, but more importantly, I knew I made a mistake because I used the product rule to check the power rule. Wow. And if you're a Maple user, if you put this function into Maple and you say, hey Maple, find the derivative, and it doesn't give you the same answer as what you worked out, then you know you've made a mistake. So you have lots of tools at your disposal to help you with checking behind you, right? And I've been doing this for a very long time and I still make mistakes. So it's important to know that you're making a mistake and know how to go fix it. But I don't know about you. I kind of think the power rule was kind of involved. Like I had to do all this multiplication and then do the power rule, whereas the product rule was a little bit easier, right? Okay, let's do one more example and then we'll jump into the quotient rule. So let's say that we have let's say y equals x to the 5th plus 2x plus 1 times square root x plus 3 over x. Okay, now we're going to call this first function f and this next one g, right? So we're going to, I am not going to multiply all that junk out. You can see why I'm not going to, right? X to the 5th times the square root of x is a very weird kind of thing, and I'd have to combine those using powers, and I kind of want to avoid that, so I'm just going to go ahead and do the power rule, right? So let me write down my power rule, product rule, my fault. The derivative of the first times the second plus the first times the derivative of the second. So let's see if we can first clean this up a little bit. Okay, so this, I'm going to use what I earlier said in the video, and that is I want to rewrite the second part using powers. So that's x to the 1/2 plus 3x to the negative 1. This is going to serve me well when I go find g prime, right? The g prime is going to be a heck of a lot easier if I have it in terms of powers. Okay, so f prime I can do real fast. Let's see, f prime is 5x to the 4th plus 2. Think about why it's 2 for a minute. Move the 1 down. X to the 0 is 1, right? And the derivative of any constant is 0, so it's 2 plus 0, right? All right, g is x to the 1/2 plus 3x to the negative 1. That's what g is. Plus, okay, f is this thing that we started with. Excuse me, my nose itches. X to the 5th. TMI, right? All right, and then g prime is this. That's the reason I did the algebra. So this is 1/2 x to the negative 1/2 minus 3 x to the negative 2. Why is it minus, Mr. Molokashka? Because negative 1 times 3 is negative 3. And why negative 2? Because I reduced this by 1. If I subtract 1 from negative 1, I get negative 2. Then, believe it or not, as crazy looking as this is my derivative. Now, if you want to go ahead and multiply it out and try to combine like terms, feel free. You can do that. You can probably let Maple do that for you very easily. But this is the work that I would need to see as your calculus teacher of how to find the derivative of a product. Okay, last rule is called the quotient rule. And the quotient rule is the worst of the three. This is definitely not a simple rule. But the rule for this is like, what happens if you have f divided by g? What if you have a rational function? Okay, if you got a rational function, you have a numerator and a denominator, right? So the numerator is f, the denominator is g. Of course, we're assuming g is not 0. But here's how this works out. So it's low d high, derivative of the high, minus high d low over low squared. And notice I haven't put the x's, right? F means f of x in this case. It could be f of t, f of theta, whatever, right? So f and g are functions of the same variable. We're not having f of x and g of theta or anything like that. Okay, so, but this is the shortest way I know of writing this rule. So low, this is the high part and this is the low part. Usually call them numerator and denominator, but it's kind of like a do-si-do or line dance, right? It's low d high minus high d low over low squared. And if you really want to get fancy, you can say low d high minus high d low over low low, because low times low, right? Low low. Okay. All right. So that's kind of what's going on. So let's do a quick example of this. You'll have to get lots and lots of practice at this to make this work out. But earlier, okay, we said, all right, what happens if y is x squared plus 2x plus 1 over x? Remember that from the very beginning of the video? Say yes? Yes. Okay. So if we simplify that, we can divide by x, we can divide by x, we can divide by x. And 1 divided by x is x to the negative 1. So this is pretty simple to do with the power rule, right? So if we cross over into derivative land, it's pretty easy to do this. This is 1 plus 0 minus 1 x to the negative 2. Okay, 1 because I moved the 1 down and now I have x to the 0. There's nothing here because the derivative of a constant is 0. And here it's negative 1 x to the negative 2, right? Negative 1 times positive 1. I didn't write the 1 there because I didn't have to. So this is, we're done, right? This is, technically this is 1 minus 1 over x squared, which you can also write with a common denominator and that kind of thing. But this is fine. This is fine right here. Now, if you did this with the quotient rule, okay, then this is your high and this is your low. So if you, this is with the power rule. Okay, so the quotient rule would say, all right, I'm just going to straight off do my derivative, and I'm going to do the low part times the derivative of the high part, which is 2x plus 2. You can pause the video if you need to think about that. Minus high d low, the derivative of x is 1, all over low squared. Done. Now, you might be asking yourself, wait, how the heck is that thing equal to just this? Well, if you work on this and you simplify it, I will show you very quickly. 1 times anything is itself, so I just have to distribute the negative sign, right, and then divide. So let's see, 2x squared minus x squared is x squared, And then the 2x and the minus 2x cancels out. And look at there. It really is the same thing, right? It really, now, they don't look exactly like each other because of the way that we arrived at the answer. But if you do enough algebra and simplifying, you'll see that they really are one and the same. And you can also graph in Maple, right, to check to see, you know, the graphs in Maple look the same. They're the same functions. Okay. Okay. Last thing I want to talk about before closing up shop for today is the tangent line problem. So let's go back to an earlier function that we were dealing with. Let's say that we had this function, square root x plus 3 over x. And we want to find the equation of the tangent line at x equals. Hey, I'm back. I know that it's a little bit weird here, but my phone rang and I just stopped the video and clipped, and a couple hours later changed clothes and came back and finished. So anyway, where I was in the previous part of this video here was to find the equation of the tangent line at x equals 1 for this function, and I'm going to remind you of something. The equation of any line, whether it's tangent or not, you might remember uses something called the point. You can use the point slope version, point slope form. If you type this in Maple, it will automatically put it in slope intercept form. So let me write that down. These are just reminders from, you know, Math 171 if you're a JCC student, or your algebra days. So the point slope form is y minus a y coordinate equals slope times x minus an x coordinate. You can also adjust this to y equals slope times x minus an x coordinate, and then take this negative y1 and move it over and just play it this way with plus y1, right? So you can do that. The slope intercept form, of course, is y equals mx plus b. So if you multiply m times negative x1 and add y1, then you're going to get your y-intercept, right? That's kind of how that rolls from your previous experience, right? Okay, so that's we're going to keep that in the bag for the way to write the answer, okay? So we're going to keep that for reference. Okay, now the calculus part of this. Okay, we're going to need the derivative, the slope of the tangent line is the derivative, which I'm going to use Leibniz notation this time, is the derivative evaluated at x equals 1. Let me say that again. It'll sound like I'm rewinding the video, but the slope of the tangent line is the derivative evaluated at x equals 1, because that's where we're taking the tangent line, right? And this vertical bar, if you will, is called an evaluation bar, and you'll see it later on in this course, even with integral calculus. You'll evaluate an integral. It'll be like a bracket instead of a vertical bar, but you'll still have numbers to put into an integral. So this is called an evaluation bar, and you'll see that again. Alright, so let me explain how this notation is going to work. The first thing I'm going to do is find out dy dx as a function, right? And if you remember from before, I'm just going to rewrite my little algebraic thing here using the powers, and then I'm going to evaluate the derivative by using the power rule. So that's what's going on here. Okay. And if I evaluate this, let me change colors here for emphasis. If I evaluate this at x equals 1, then I'm evaluating this at x equals 1, which means I'm putting 1 in the place of x. That's all I'm doing. So that's going to be 1/2 times 1 to the negative 1/2 power minus 3 times 1 to the negative 2 power. And we all know that, I should make that a little bigger when I'm highlighting, this and this is exactly 1, right? 1 raised to any exponent. Let me go back and try that again. 1 raised to any exponent is 1, right? So that makes this problem pretty simple. We get 1/2 times 1 minus 3 times 1. Whoops. Hit a button I shouldn't have hit, my bad. Which is 1/2 minus 3, which is 6/2, for a grand total of negative 5/2. Okay, so that is our slope of the line, right? That's our slope. Now, let's circle all this, and we'll call that M. That's our slope, right? Now, we need a point. Okay, so let me go change colors here and find a point that's on the line. And we already know the x-coordinate of the point, right? But what we need is the y-coordinate, and the y-coordinate is going to come from here. This is what tells us our y-coordinate. So in order to get the point, hopefully you're getting the point, haha, we know that x is equal to 1, so what we're going to do is we're going to evaluate the function. We're going to evaluate the function at x equals 1 instead of the derivative. Remember I said earlier in the video, right? The function is one thing, the derivative is a completely different thing. The function tells you the y values on the graph. The derivative tells you the slopes of the tangent lines at all those values. Okay? So I'm having to do two things at once, right? I have to evaluate the slope, which is dy dx at x equals 1, and then also the value of the function y, right? All right, so this is going to be the square root of 1 plus 3 over 1, which is 1 plus 3, which is 4. All right, so the point is our x1, y1, if you will, right? And that is the point 1, 4. Okay, so now that we've got all that stuff, we can find, I'll use the point slope version. I'm going to say y minus y1, remember we just found out to be 4, right, equals the slope, which we found out to be negative 5/2 times x minus 1. Okay, so the answer to this isn't a perfectly acceptable answer. It works. Another version of this answer would be this. In fact, this is the one I'm going to use when I type this in Maple in just a moment. And or if you go ahead and do the distributive property and add this, if you want, you can do slope-intercept form. So let's see, that's going to be 5/2 plus 8/2, which is 13/2. So any of these are acceptable answers, and if you want to work smarter, not harder, stop right there, right? Okay, now what I'm going to do is I'm going to illustrate, I'm going to graph a couple of things, okay? So let me go highlighting. I'm going to graph a couple of things. I'm going to graph this function, and I'm going to graph, well, this line. Actually, I'm probably going to use this one. I like that version the best because it has y by itself. And I'm going to put both of these yellow things in Maple. So pause the video and write both of these things down if you need to. But I'm going to go ahead and type them in Maple. Okay, so let me hide all that, and we'll go take a look at Maple. This version of Maple should be the same version that my students have downloaded for JCC for the fall 2021 semester. And it doesn't matter whether you use a document or worksheet. I always use worksheet. In the beginning, there's a little link that tells you which you should choose. But I'm going to just use Maple as my visual tool to check things, right? And what I want to do is I want to call up the plot builder. So I'm just going to start typing words like plot, right? And like for example, I can call I don't know, y equals square root x. By the way, I am not a Maple expert, but I can get by, right? I remember when I was a freshman at NC State back in 1991, yes, 30 years ago this semester, I was a freshman at NC State. I had to use the very first version of Maple that ever was created, like the early versions of Maple. It goes back that far. Yep, it sure does, but I haven't used it that much in the last 30 years. Anyway, if you start typing a function, like even just y equals square root x, you'll see plot builder that comes up, right? And so once plot builder comes up, I'm not able to get very much, right? I'm like, it doesn't look good. I can't do anything, right? So like, okay, this is no bueno, right? So one of the things I can do is finish typing this function up here. Let's see, plus 3 over x, right arrow key, comma, and I'm also going to do y equals the tangent line, which is negative 5 halves times. It's important to do the times. If you just put a number with parentheses, sometimes Maple doesn't realize that you're having to multiply. So you have to do times x minus 1, and then add the plus 4. Okay. Oops. What happened there? Okay. I must have hit enter by accident. All right. So I can hit enter, and there it is, right? And I'm going to do the plot builder. And there's a couple of things I can do. Implicit plot, or I can do like inequality, but doesn't look too good, right? So I'm just going to escape out of this. And I'm just going to go to plot builder on its own, right? Okay, so now that I've got plot builder on its own, I guess I just had to keep fumbling around until I could get plot builder to work. For whatever reason on a Mac, it's a little finicky. But anyway, once you get the plot builder tool to come up, you can put in your functions. So I'm going to type in sqrtx. Whoops. Let me add a function and call it sqrtx plus 3 over x. Let me go add that. And I don't want a graph 2, so I'll remove that one. And I'm going to go add the tangent line. So what was that? That was, and by the way, if you look up here, you can see that Maple has done the slope-intercept form for me. But you know what? I'm just going to type in the old school one, negative 5 halves times x minus 1, all right, plus 4. So I'm going to, oops, I need to close my parentheses there. There we go. And hit accept. Hopefully, yep, and it did it again. It made slope-intercept form for me. So once I've got both of the expressions in there, I want a graph. Then I'm just going to hit OK. And I want to do 2D plot. I don't want any weird complex plots or parametrics or anything like that. Now, you might want to control the x-axis ranges. Remember, I want the slope of the tangent line at x equals 1, so I don't need to see all the way from negative 10 to 10. Maybe negative 5 to 5 will be good. And I can preview this, and there it is, right? I can screenshot this and put it in my lab or whatever. But sure enough, at the point 1, 4, that was the point on the graph, this is the line that is tangent to the curve. And the curve, you know, square root x plus 3 over x is that curve, and in the first quadrant at least. And there are no other quadrants, I don't think. You can't use negative numbers for x or even 0, so x has to be positive, and there you go. But you can see, like visually, like you have the graph and you have the tangent line, and they do appear to be tangent. So if you go graphing both of these things in your plot builder in Maple, there are tons of other ways to put both equations on the graph in Maple. You can research those, you can use the tutors or whatever. But you can visually see in Maple, and now that I've previewed that, I'm just going to say, you know what? I'm going to go ahead and put that in my workbook, right? And so then if I want to, you know, do something with this graph later on, I want to call up a command to do a derivative at x equals 5 or something like that, I can use Maple to do that. All right, so a little preview there of, you know, checking your answer, the function against the tangent line, and you can do that in Maple. All right, last thing, and I probably said last thing already, but if I did, I lied. Sorry about that. But there is one more thing I want to remind you of, and that is the multiple derivatives. So, you know, let's say that, wow, that's way too big. Try that again, Mr. Molikash. There we go. Let's say that you have y is equal to, you know, x to the 15th, just by itself, right? Using the power rule, you should know that the first derivative of this is 15 times x to the 14th, right? Need a little bit extra on the power rule, go back and watch that part of the video again. But you can take the derivative of the derivative. It's called the second derivative, and that would be 15 times 14, which, let's see, what is 15 times 14? That's 210. It's the same thing as 30 times 7, right? And that would be x to the 13th. And yes, you can even do the third derivative, and after that you start putting parentheses like that. You don't have like the 15th derivative with 15 primes on it. That's kind of bizarre. So after the third derivative, I think the notation, especially when you get into calculus 2, you'll have to do derivatives up to the 4th, 5th, and 6th derivative and so forth when you're doing power series. But for us, you know, we'll do first, second, third derivative. Okay. Why is this important in the practical sense? Well, it's important because let's say that this is a position function, going back to my previous video, right? The first derivative of position would give you instantaneous, not average, but instantaneous velocity. So at x equals 1, y equals 1 meter maybe, but at x equals 1, y prime would give you 1 meter per second, or 1 mile per hour, or 15 miles per hour, 15 meters per second. You know, this would be units that we would use, right? So, you know, for position, you'd have units, and this would be units over time. You know, so, you know, meters per second, miles per hour, whatever. And then the second derivative of position, or the derivative of velocity, tells you the instantaneous, if I can spell this out, acceleration. And acceleration would be, you know, meters per second per second. So, you know, if this is meters, this would be meters per second. And then maybe if you remember your physics class or whatever from high school, this would be meters per second, or meters per second squared. And, you know, the acceleration due to gravity is like 9.8 meters per second squared, right? So that's how fast something accelerates if you just drop it with no air resistance. This would be how fast it's moving and directionally, and this is where it is at a specific time. So you could see that Sir Isaac Newton was really interested in physics, and he used calculus to figure out physics, right, problems. So this is an important, I guess, application of repeated derivatives, first, second, third derivatives. This is Lagrange's notation. If you had Leibniz notation, it would look like this. You'd have dy dx, and then technically your second, that would be this. Your second derivative would be the derivative of the derivative with respect to x. Wow, right? The derivative of the derivative with respect to x with respect to x. That kind of looks weird, so what we say is we have two d's on top, and then there's two dx's on the bottom. So this is what the Leibniz notation looked like earlier in the video, if you remember the Wikipedia page, and again I'll link that in the description, but this is your first derivative, and then this is your second derivative, and your third derivative would be the derivative with respect to x of the derivative with respect to x of the derivative with respect to x. Wow. So up top you'd have 1, 2, 3 d's, right? And on the bottom you'd have 1, 2, 3 dx's. So that would be the Leibniz notation for the third derivative, if you needed it, right? Now, the third derivative, if you look this up on, I don't know, Wikipedia or Google, the third derivative of position is called the jerk. It's called the jerk, and I think about, like, I used to drive when I was younger, I used to drive a manual transmission, and if you forget to push the clutch in before you put it in gear and you start the car up, you get a jerk, right? So a jerk is an instantaneous change in acceleration, right? That's the way to think about it. It's actually called the jerk. It's funny. There's a movie called The Jerk with Steve Martin in it. But anyway, that's a little overview of multiple derivatives and how it works out with physical quantities, position, velocity, and acceleration. So I hope this has worked out for you. I know this went really fast. I would encourage you to go back to different parts of the video and slow down and take notes. Please reach out to me if you have any questions. I'm definitely here to help. So hang in there. I appreciate you continuing on with me in this wonderful endeavor we call calculus, and I hope you have a great week.